Hey guys, today we're going to talk about other bases other than E and some of those applications. So the base of the natural exponential function is E. This natural base can be used to assign a meaning to the general base A. So definition. If A is a positive real number, A is not equal to 1. And the reason we don't want A equal to 1 is 1 to any power is just 1. That's boring. Okay, and x is any real number, then the exponential function to the base a is denoted by a to the x power and is defined as this. A to the x equals e to the natural log of a times x. So if you think about it, if I use my properties of x or of natural logs, x times the natural log of a really means really means the natural log of a to the x power. And then if I have an e here like this, well, the e and the natural log cancel out, and I just get a to the x equals a to the x. Okay, so those are the same thing right there. If a is 1, then y equals 1 to the x, which is just 1 as a constant function. Okay, so these are familiar properties. We kind of talked about these with the natural base as well. Anything to the zero number is 1, or to the zero power is 1. A to the x times a to the y is a to the x plus y power. I went through that before. A to the x divided by a to the y is a to the x minus y power. And a to the x to the y power is just a to the x times y power. So I guess I can run through these again real quick here. If I had something like a to the second times a to the third, that would just be a times a times a times a times a, which would be a to the fifth, which would be a to the 2 plus 3 power. So this works here. Same thing here. If I had, say, a to the fifth divided by a to the third, this would be a times a times a times a times a over a times a times a, and then those would cancel, and I'd be left with a squared, which is a to the 5 minus 3. And then over here, this would be like a squared to the third. Okay, so this would be a squared times a squared times a squared, which would be a times a times a times a times a times a, which is a to the sixth, which is a to the 2 times 3 power. So that's why all those work. All right, radioactive half-life model. So the half-life of carbon-14 is about 5,715 years. A sample contains 1 gram of carbon-14. How much will be present in 10,000 years? Okay, so here's what we're going to do with that. Is we're going to write down an equation, y equals 1/2 to the x over 5,715. This is going to be the formula. Here is our half-life, okay? So we're going to have half every time we have 5,715 years go by. And then I'm just going to substitute in 10,000 for the x. So I'm going to have not quite 2 half-lives. So I should have approximately a quarter of what I started with. Okay, because my first half-life would give me half, and then half of that would be a quarter. Okay, so let's plug it into our handy-dandy TI-84 plus C Silver Edition graphing calculator. 0.5 to the 10,000 divided by 5,715 power. Bam! That's going to be approximately 0.2973 grams. So we didn't quite have 2 half-lives, so we got a little bit more than a quarter that's left. Okay. All right, definition of a logarithmic function of base A. So if A is a positive real number and it's not equal to 1, and x is any positive real number, then the logarithmic function to the base A is denoted by the log base. This is read log base A of x, and is defined as the log base A of x equals 1 over the natural log of A times the natural log of x. Okay, so some functions. Log base A of 1 is 0. Any log of 1 is 0. The log base A of x times y is the log base A of x plus the log base A of y. This is all the same rules as work for natural logs. Log base A of x to the n is n times the log base A of x. Log base A of x divided by y is the log base A of x minus the log base A of y. This is all review too from pre-calculus. All right, inverse functions. If y equals a to the x, if and only if x equals the log base a of y. So remember the phrase, logs are exponents, right? So this is a log, which means this is a log, and that is an exponent. Okay, so you can move back and forth between these two, whichever one's convenient for you to use. Most of the time, people will take an equation like this and they'll turn it into something like that, because it's easier to solve. A to the log base A of x equals x. So if I want to get rid of a log of base A, I just take A to that power, and that cancels out, and I just get x. Log base A of A to the x equals x. The logarithmic function to the base 10 is called the common log function. So that's the one that you see on your calculator. It just says log, that's your common log. It's automatically log base 10. Common logarithms, y equals 10 to the x power if and only if x equals the log base 10 of y. Okay, solve for x in each equation. So here's what I can do here is I can say, well, I want to get rid of that base 3, so I'm going to take the log base 3 of 3 to the x on both sides. Okay, now this cancels, and I get x over here. And the log base 3 of 81, let's see, that's going to be, negative 4? So it's going to be negative because I need to flip it over, and then 3 to the 4th power is 81. Okay, the log base 2 of x is negative 4. So on this one, I want to get rid of the log base 2, so I'm going to take 2 to that power on both sides. That makes this cancel out. I get x equals 2 to the negative 4 power, which is 1 over 16. Okay, derivatives. So the derivative of a to the x power is the natural log of a times a to the x. The derivative of a to the u power is, the derivative with respect to x of a to the u power is the natural log of a times a to the u times du dx. The derivative of log base 10, log base a of x is 1 over the natural log of a times x. And the derivative of the log base a of u, the derivative with respect to x of the log base a of u, this should have a closing bracket there. That's 1 over the natural log of a times u du dx. Okie doke. So find the derivative of each of these functions here. Okay, so if we use our formula, y prime is going to be 1 over the natural log of 2. I'm sorry, just the natural log of 2. Natural log of 2 times 2 to the x. And I can't really do any more to that. Okay, the next one. Y equals 2 to the 3x. Now I'm going to have the chain rule involved here. So other than that, it's going to work the same. So y prime is going to be the natural log of 2 times 2 to the 3x times 3. And you could just leave it like that. A lot of people will clean this up and put the 3 out here in front. Okay. So now we've got y equals the log base 10 of cosine of x. Okay, so with our formula, that's going to be 1 over the natural log of 10. I'm sorry. 1 over the natural log of 10 times cosine. Whoops, the cosine on the bottom. And then I got to take the derivative of cosine, so that's going to be negative, it's going to be negative sine. So I'm going to get negative sine x over natural log of 10 cosine, natural log, negative sine x over natural log of 10 times the cosine of x. And then the sine over the cosine is just the tangent. So this is going to be negative tangent x over the natural log of 10. Okay. Now, what about this bad boy right here? So we've got y is the log base 3 of the square root of x over x plus 5. Okay, so this is one that I would break this up a bit because we're in logs, so we're going to take advantage of logs. So we're going to change this equation to y equals 1/2 the log base 3 of x minus the log base 3 of x plus 5. So there's we're using our properties of logarithms to change this equation into something that's easier to take the derivative of. Okay, so now this, if I take y prime, this is going to be 1/2. This is going to be 1 over the natural log of 3 times x. And that's on the bottom right there. So there's the first part of this equation. Now the second part is going to be 1 over the natural log of 3 times x plus 5. And now we can find a common denominator here, and we can combine those. I mean, this is the answer. You could leave that and you're going to get credit, but if you wanted to clean this up, I'd need to multiply this one over here by, I'd need a 2 and an x plus 5. Nope, I'm sorry, an x. It's going to be a 2x over 2x. And this one is going to be times an x plus 5 over an x plus 5. Okay, so that's going to give me a denominator that's 2 natural log of 3 times x plus 5. And then I'm going to have an x plus 5 minus a 2x. And so then I can clean that up again. X minus 2x is going to be negative x. This is going to be 5 minus x on the top. And I'll have a 2 natural log of 3 times x plus 5. And we'll call it good. I suppose you could distribute that if you wanted to, but why? Okay, occasionally when using an integrand involves an exponential function to a base other than e. When this occurs, there are two options. So convert to a base e using the formula a to the x equals e to the natural log a times x, and then integrate, or integrate it directly. The integral of a to the x dx is 1 over the natural log of a times a to the x plus c. Okay, so now we're going to find the integral of 2 to the x power dx. Okay, so this is going to be 1 over the natural log of 2 times 2 to the x plus c. And you can't really do anything else with that, so we're just going to leave that as the answer. Okay, the power rule. So the derivative of x to the n is n times x to the n minus 1. So we've been doing this since almost the beginning of the year. The derivative with respect to x of u to the n is n times u to the n minus 1 times du dx. So remember this. This is a real simple formula that you've used all year. So let's look at some of these. So comparing variables and constants. So the derivative of e to the e is 0. So if you think about this, why does that work? Well, e to the e is just a constant. So this would be like, what's the derivative of 3? It's 0. Okay, the slope of the line 3 is 0. It's a horizontal line. Well, this is a horizontal line as well, so the slope is 0, so the derivative is 0. We did this last time. The derivative of e to the x is e to the x. The derivative of x to the e is e times x to the e minus 1 power. Okay, what about y equals x to the x power? Okay, so this is one where we're going to take the natural log of both sides. So that lets me take my power down. Okay, and now we can take the derivative of that. So remember, the derivative of this is going to be y prime over y. And then we're going to have the derivative, we're going to use the product rule here, so it's going to be 1 times the natural log of x plus x times the derivative of the natural log of x is going to be 1 over x. Okay. And so then this is just going to be 1. So y prime over y is going to be 1 plus the natural log of x. And then I got to move the y over here because I want y prime. I don't want the y prime over y. So it's going to be y times 1 plus natural log of x. And then I got to go back up here and say, oh, y was x to the x. So y prime is going to be x to the x times 1 plus the natural log of x. So that's not too difficult. Okay, applications of this. So we did this last year as well, compound interest. the amount of P dollars is deposited in an account of an annual interest rate of R. What is the balance of the account at the end of year 1? The answer depends on the number of times that N is the interest is compounded according to the formula. Okay, so here's our formula. Remember, A stood for amount. That's how much you have at the end. P stands for principal. That's how much you deposit or how much you initially borrow. R was your interest rate, expressed as a decimal. N was the number of times your money is compounded per year. And then for some reason missing here is a T, which that T stands for time in years. So I know why the T was left off, is that was just 1 year, so the T is 1. A limit involving E, so the limit as x goes to infinity of 1 plus 1 over x to the x is the limit as x goes to infinity of x plus 1 over x to the x, which happens to be E. So find the amount after 1 year of continuous compounding. Okay, so what that does is that takes this formula right here and it converts it into continuously compounded interest, which that formula is A equals P e to the RT. Okay, again, P is principal, R is interest rate, T is time, E is just the number E, and A is the amount. So if we want to find the amount of $1,000, at 8% interest for 1 year, compounded continuously, there's my problem. Got it all set up. 1,000 times e to the 0.08 power means that I'm going to have $1,083.29. Okay, so here's my two compound interest formulas. Compounded continuously, compounded any other time. So, if this was compounded daily, this would be 365. If it was compounded monthly, it would be 12. If it was compounded weekly, N would be 52. Compounded quarterly, N would be 4, and so on. So a deposit of $2,500 is made in an account that pays an annual interest rate of 5%. Find the balance of the account at the end of 5 years when the interest is compounded quarterly, monthly, and continuously. Okay, so for the first two, quarterly and monthly, we're going to use this formula. A equals P times 1 plus R over N to the NT power. For the compounded continuously, we're going to use A equals P e to the RT power. So both of these, the principal is going to be $2,500. Okay, and then A is going to equal, all right, my rate is 5%. Okay, so that's going to be 0.05, and this is going to be e to the 0.05 right here. And then compounded quarterly, so that's going to be 4 for N. That does not apply to this. Okay, and then T is time in 5 years. Where was that? End of 5 years. Okay, so T is going to be 5 on both of these. Okay, So now I just got to figure out what these are. So we'll start with the inside here, 0.05 divided by 4. It's 0.0125 plus 1. So this is going to be 1.0125 to the 20th power times 2,500. So this comes out to be $3,205.09. That's compounded quarterly. Now, I also needed to do this problem compounded monthly. Okay, so if I compound it monthly, it's pretty much the same problem, 2,500 times 1 plus 0.05, only monthly is going to be, n is going to be 12. So I'm taking a less interest, but I'm compounding it more times. So 0.05 divided by 12 plus 1 is going to be 1.00416 repeating to the 60th power times 2,500. So that comes out to be $3,208.40. So that's compounded monthly. So you can see I got a little bit extra interest by compounding it monthly rather than quarterly. Now over here, this would be as if I was compounding it instantaneously. So 2,500 times e to the 0.05 times 5 power. So this one comes out to be $3,210.06. That's the most interest you can get at that interest rate in that time frame without bumping up the interest rate. So you can see it's a little bit more than that one because you've compounded it an infinite number of times more. Okay, bacterial culture growth. So a bacterial culture is growing according to the logistical growth function y equals 1.25 over 1 plus 0.25 e to the negative 0.4 t, where t equals 0, where y is the weight of the culture in grams and t is the time in hours. Find the weight of the culture after 0 hours, 1 hour, 10 hours. What is the limit as t approaches infinity here? Okay. So we're going to go ahead and plug in 0. And so we'll call this y of 0. So that'd be 1.25 over 1 plus 0.25 e to the negative 0.4 times 0 power. All right, well that's just going to be 0. That's going to be e to the 0 power is going to be 1. This is going to be 1.25 over 1.25, which is going to be 1. Okay, which makes sense. At times 0, we have whatever it is we started with here in grams. So we have 1 gram. Okay. Let's make some room here. So now let's try at 1 hour. So this would be y of 1, 1.25 over 1 plus 0.25 e to the negative 0.4 times 1. Well, that's just going to be to the negative 0.4 power. So 1.25 divided by, open parentheses, 1 plus 0.25 e to the negative 0.4 power, and then we'll close the parentheses, and that comes out to 1.0706 grams. So this grew a little bit. Now let's look at 10 hours. So y of 10, 1.25, 1 plus 0.25 e to the negative 0.4 times 10. So that's basically the negative 4 power there. 1.25 divided by, open parentheses, 1 plus 0.25 e to the negative 4 power. Okay, so y is going to be 1.2443 grams. Okay, what is the limit as t approaches infinity? Okay, so what you could do is you could plug this equation right here into actually this equation right here into your graphing calculator, and you could make a table and see where that goes. And what you're going to find is that this is going, as this gets bigger and bigger and bigger, as t gets bigger and bigger and bigger, this ends up right here approaching 0. And so this ends up to be 1.25 over 1, which that limit is going to end up being 1.25 grams. So we would say the limit as t approaches infinity of 1.25 over 1 plus 0.25 e to the negative 0.4t. Is going to be 1.25 grams. And here's your assignment. So a lot of this will be review for you. You shouldn't have too much trouble with it. And I will see you next time.